Okay, let's get started. I apologize, we're starting a few minutes late. Vice President Biden kept emailing me this morning. He wanted to learn a little bit more about mental models and memory, attention, and perception. I kept asking if he'd registered for this class, and he's trying to claim he didn't need to because he was the Vice President. He's not here. Okay, so let's carry on. We are working our way through our section on cognitive psychology, and we've organized these 4 lectures from things that are that we're beginning in the neuroscience field to nail down, and things that are a little bit more hand-wavy. So we started last time talking about mental models, otherwise known as forward models. Why are they called forward models? You have tons of them in your brain. So, but they're making predictions about something that's going to happen in the future, right? I do something and I expect to see something or hear something or feel something 1/10 of a second from now, a second from now, a week from now, a month from now, a year from now. So there is growing evidence that we can actually measure these forward models in the brain. We're going to get into memory, attention, and perception today. These are things that we know we are capable of, but they're a little bit more hand-wavy. How they're actually instantiated in the brain, we're not quite sure. We're going to talk later next week about Gestalt perception and the frame of reference problem, even more hand-wavy. And then finally, we'll get to affect, otherwise known as emotion. Again, we all know we have it, but exactly what it is and how or whether we would ever want to instantiate affect in machines, we'll see. Okay, so before we get back to lecture 11, any questions about deliverable 8? I see that most people managed to get something submitted for deliverable 7. Anybody still working on deliverable 7? A couple people? Okay, all right, we'll get there. So most people, I think, have got something instantiated. Yes?
Well, why is there no quiz today?
There's no quiz today because I have some colleagues visiting from another university and we've got some research meetings, so I won't have time to put together a quiz for you today. So Friday afternoon, no quiz today.
You're meeting with Biden, right?
It's the meeting with Biden. Yes, that's right. Okay. All right. No questions about deliverable 8? Yes?
Did you post it?
I posted the PDF, and now that you say that, the submission for deliverable 8 is not there. Can you send me an email to remind me? I'll make the submission. The PDF is there, so you can get started on it. I'll put it up on Blackboard.
Yeah,
Bit of a crazy.
I via the schedule. That's how I saw it.
Yeah, you can see it. Yeah, exactly. Just click on it from the schedule, and it's all there. I'll put it on Blackboard later today. Okay. Okay. So finally, lecture 11. We introduced the evil starfish last time, and the reason why we were talking about robots in an HCI class is because this particular robot gives us unique insight into how an agent, which may be a robot or a human user, forms mental models or forward models. They do it by interacting with the world, pushing against the world, and observing how the world pushes back. And every time you do that, you get a training instance. You push against the world a whole bunch of times. You now have a training set, and you use a machine learning algorithm to produce a mental model. And you can now use that model that when you think about pushing against the world, you don't literally push against the world. You submit that action to the mental model, and the mental model gives you back a prediction about the sensory repercussion forward in time of that action. Right? So obviously, mental models are very useful for robots and humans alike. They allow us to avoid dangerous situations and mentally simulate something without having to try it in reality. So mental models are good because often mental models might die in our stead. Okay, so back to HCI now. Obviously, in HCI, it's all about people, and different people use the same system in different ways, so they form different mental models. So your grandmother goes to buy you an MP3 player at Best Buy. For her, if it's anything in the shop that plays something called an MP3, then it's an MP3 player, right? That's it. So as she looks at devices, making predictions about is this an MP3 player or not, that's the bar to pass. For other users, they might be a little bit more discriminating, right? Is it actually an MP3 player, and so on. Okay, Different people obviously push against applications or systems in different ways, right? So if I want to learn about this system and build up a mental model of the new smartphone that I got, I'm going to start to navigate through the menu hierarchy and my mental model that I built up from using smartphones over the years. That mental model makes a prediction about where the function called send new message is located in the menu hierarchy of my new phone. So rather than clicking at random through the menu hierarchy on my phone, I'm being much more selective and I'm being directed by my mental model, which is making expectations about where to find it, right? Okay, so where's the turn off new message alarm? My mental model predicts it's either in the messages or the options submenu. And as we do, I'm starting with my existing mental model and now I'm adapting it for the new system, right? So we're always building up and adapting our mental models as we go. How do we build this up? Well, in essence, what we're doing is reducing uncertainty with each action we perform. So in this example here, I have some uncertainty about where this particular function is. It's either in messages or options. So maybe I flip a coin and pick one. And if I don't find that functionality in messages, I've increased the certainty that it's in options. So we're going to come back to the robot in a moment and see how it also reduces uncertainty. Okay. Another set of your users, the early adopters, they'll just go through the entire menu hierarchy. They want to know everything that the phone can do. So they're not really using a mental model. They're just doing brute force search, right? What is everything that I can possibly do with this new phone or this new app? Different people have different mental models and use them to push against the system in different ways. Okay. So again, obviously we do this. How do we build up a mental model? By playing around with the phone or the app and seeing what it presents to the screen or what sounds it produces. And then there's a process that we follow. And the first one is usually rote learning. You've got a brand new application. You just kind of remember where everything is, right? So in this cartoon example over here, you've entered into n interactions with the system. And you've got n different responses back, but you start to notice that these responses tend to fall into one of two classes. So I see that some of you have built into your ASL system now an interaction that will flash a big green check mark to the screen or a big red X. So I'm playing around with your system, and I see that most of the time I'm getting either a check mark or an X, and I'm not really paying attention to why or why not. I'm noticing that there are those two main sorts of things that your system gives me back whenever I interact with it. Okay. Most people at some point will then use that to embark on conceptual compression. So I learn something about the underlying conceptual structure of this new information space, that there are two conceptual objects, right and wrong, or correct and incorrect. And there are certain things that I can do that result in correct, and there are a bunch of other things I can do that end up in incorrect. So you don't need to print to the screen. This system will look at your hand and figure out whether you're signing the digit that's being printed to the screen, right? Hopefully, given the kinds of system you're setting up, most users might start by waving their hand more or less at random, getting a whole bunch of things back and realizing that there are certain things they're trying to do. They're trying to do this thing that results in the correct repercussion and avoid the things that leads to the incorrect repercussion. Years ago, when my father was trying to learn how to use computers, he is definitely not a tech guy. He definitely didn't want to use computers, but he likes to write, and he realized he eventually had to give up his typewriter and use this newfangled thing called a word processor, which wasn't so newfangled at that point. I sat down, took a deep breath, and tried to teach him how to use a word processor, and I said, if you want to type on the screen click open, click file, click so on. I wrote it on a Post-it note and put it over his desk. If you want to save what you've written, click on this, then click on this, then click on that. And by the end of this, we had about 30 or 40 Post-it notes in front of him. He was never able to conceptually compress that into the underlying structure of what a word processor really did. He would just sit down and follow by rote these Post-it notes. As you can probably tell from me telling you the story, it didn't end very well. Why not? We don't live in the same city, so I started to get a lot of phone calls.
I didn't understand why you went through steps.
He told me he didn't care. I don't want to know why this computer is doing this. I just want to print what I've written so far. Write me a Post-it note about how to print what I've written so far. I don't care why, just what do I do to print? What's the problem that you can imagine arose? None of you have parents or grandparents where you've gone through this process with them?
I give more hardware questions than software questions.
Okay, fair enough.
The ability to do something doesn't equate to understanding. And so if you get to a point where your ability doesn't match up with what you need to do, there's no understanding to fix that kind of problem.
If something comes up, right, so he deleted something and he wants to undelete it, and there isn't quite an exact Post-it note that corresponds to that situation, I get a very agitated phone call.
It's like the whole teach a man to fish thing, right? You tell him how to do it, you can do one thing, but you teach him how, and then he'll do other.
Absolutely, right? So my father could, in most cases on a good day, do N things, but not learn how to do the N plus first thing. Exactly, right? That's why, aside from the fact that most of us in this room probably just like technology, you bother trying to figure out the underlying structure. Once you know how a system works, you can usually figure it out on your own. And if the interface is good, you can usually get it right on the first try, right? Okay, so obvious drawback of rote learning, you can't figure out how to do something new or extricate yourself from a new error message or a new problem, right? You can't predict what will happen if I do this, or if you get some new repercussion, some new error message or some new message, you can't reverse engineer from this novel result what you might have done to cause it and thus undo it, right? Okay. Different users are going to make it further along this process than others, given your system. Okay. Okay, so we're now in the section in cognitive psychology. Psychologists in general love optical illusions, so we're going to get the first one in a moment. Has anyone seen the Necker cube before? This is one of the most famous ones in psychology. Okay. So when you are interacting with the physical world or an app, you're building up a hypothesis for what's going on inside the machine. What is the thing that is taking some stimulus from you? It's receiving a key press or a gesture, and it's giving you back a response. As you're doing this, you're interacting with the system, you're building up a mental model of what's going on inside the app, right? Okay. Let's take a very, very simple example of this. This is the Necker cube, and I'm going to stop talking for a moment. And I want you to just kind of relax and focus on the Necker cube. And as you do, I want you to not think consciously about the answer to this question, which is which square is closer to you. I want you just to try and allow your brain to tell you which face is closer to you. Okay. Which face is closer to you? The square in the bottom left or the square in the top right?
It changed.
It changed. Well, you know the real answer, which is neither, right? So that's why I asked you to relax and not consciously try and answer the question. Your prefrontal cortex, the part at the front is saying the professor's crazy. Why is he asking me this question? I know it's neither. But the back of your brain, which is where you're receiving the visual stimuli, is telling you something different, right? It's telling you that you're looking at a three-dimensional object. You said it changed. Did it change for others? Try and describe for me how it changed.
Like 90% of the time for me it was the lower square,
Ah.
and then every once in a while it would switch
Okay.
quickly and then go back.
Okay, so there have been lots of studies of this. So for some people, it's an asymmetry. They see more of one front-facing side than another. For others, it's about 50-50. You said sometimes it switched. Did anyone experience the rate at which it switched? Did it feel like it was going like this?
Well, at first I always saw like bottom left being in front,
Okay.
and then like after a little bit when it switched to the top right one, then it started to happen more often. Like it's sort of like exponentially, I guess. I get to go back and forth.
Once your brain was able to interpret it as the top right being closer, now you have two hypotheses, right? Your brain says it may be the bottom left or it may be the top right. And hopefully most of you started to experience this alternation, right? For most people, it feels like, after a while, it feels like it's alternating. Yep.
For me, it was when I first saw the bottom left one, but as I looked up, like at the other corner of the top right one, that's when it started to switch for me. And now every time I move through like that very central little square, it switches.
Okay. So as you looked up, right, or as your eyes passed the small square in the center, you were obviously not pushing against this cube, right? You're sitting passively, but you are interacting with the Necker cube in a very important way. There are muscles in your eyes that are causing your eyes to saccade or move to a different place on the Necker cube. That is you figuratively pushing against the world. How does the world push back? It does. So you move, and remember the world pushes back because it gives you some new sensory stimulation. Every time you act in the world, your sensoria, all your 5 or 6 senses, depending on how you count, register a change. What's the change? How did the world push back? No?
Oh.
Yep.
I was just gonna say, like, just the way you perceive it. So
The way you perceive it, that changes, but even before we get to perception. You are looking at, let's say, the very bottom left corner here, and you flex some of the muscles in your eyes, which took your focal point to the upper right. What happened?
the box chip switched.
Well, before we even get to the box switching, you pushed against the world.
The distance of the bottom left got further away.
The distance of the bottom left got further away, right? So the pattern of photons that are falling on your eye is different, right? You sat there for a few seconds doing this. You're building up a training set. If I look at this point and I send muscles to try and send my eyes to focus on this point, before your eyes get there, which takes about 1/10 of a second, that's the length of a saccade. Before you get there, you have mental models up there that are making predictions about what you're going to see when your eyes get there. Were your predictions supported? Did you see what your brain was predicting you would see? This is where things get a little tricky. The Necker cube is a very simple thing, but it has a lot of these subtleties. Let's imagine you're looking down here, and let's say you're looking at an actual three-dimensional cube in which this lower left face is actually closer to you, and you saccade up here. What would be different from what you would see in that actual 3D cube compared to the Necker cube? It would be very similar. The prediction of your mental model is going to be pretty close, but it's also off by a little bit. Why?
Well, part of the back square wouldn't be visible.
That's true. There's an occlusion. Okay, let's say it's a physical cube that's made out of a bunch of straws. No occlusion. What's different between this drawing of a 3D cube and an actual 3D cube? Any arts majors here?
There's actual depth in the 3D cube,
Which means,
so we can physically determine points location in space.
yes, how? So you're looking at an actual 3D cube rather than a two-dimensional representation of a 3D cube.
Its relation to another point on the cube.
Yes, exactly, right? So perspective. That back cube would seem a little bit smaller to you for any three-dimensional cube because it's further away from you, right? Things that are further away are smaller. Your brain has 20 or 30 or 40 years of that experience. No actual 3D cube, if it's actually a cube, has ever violated that expectation. The Necker cube does. So your prediction is frustrated a little bit. So your brain says, whoa, 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 this seems to be a cube, or it seems to be a cube in which the lower left face is closer to me, but my prediction is not matching up with the actual data that I'm getting back. Like your KNN learner that predicts one thing and the reality is actually something else. So your brain says, this hypothesis, I have one hypothesis. I'm looking at a cube with the lower left face closer, and that hypothesis doesn't seem to be standing up to the tests that I'm performing. I'm looking down up here, so is there another hypothesis that maybe explains what I'm looking at? Which is, what's the other hypothesis? That you actually are looking at a cube, but now it's the upper right face that's closer to you, right? So now your brain does the same thing. It says maybe it's that second hypothesis. I'm going to now make a prediction. I'm going to, in a moment, saccade and look back down here. And your mental model yet again makes a prediction. Your brain is a prediction machine. It's doing it all the time. Makes a prediction about if this upper right face is closer to you, you should see a certain pattern when your eye gets down here. What happens when your eye gets down there?
The bottom one.
Right. So that hypothesis didn't stand up. It's off by a little bit. Your brain says, shoot, that hypothesis didn't work either. What else is there? There really are only two kinds of hypotheses that exist here. So I don't know if you were aware of it or not, but while the cube was doing this in your mind, your eyes were also jumping around the picture. You were forming and trying to support hypotheses and collecting evidence that frustrated that hypothesis, and around you go, right? It's kind of subtle, but that's what you're doing when you're interacting with the real world or an app or anything. You're forming these hypotheses. Okay, I found this functionality. Based on the fact that I found this, I predict this structure for this app, which tells me that I'll probably find this other functionality, which I haven't seen yet, at this other place in the system. Oh, it's not there. I guess my understanding was wrong. There must be something else going on here. Okay, this is the heart of mental models. You have them, you build them, and you build them by forming hypotheses, and you form hypotheses by pushing against the world and observing how the world pushes back. Okay, so let's move on a little bit now. We're going to look at different kinds of cognitive architectures, and this is where the hand waviness starts. So cognitive architectures, if you look at any psychology textbook, tends to look something like this. You have a bunch of boxes and arrows. This is a sketch of what your brain is doing. This does not in any way correspond to the actual reality of what's going on in your brain. So just hold on to that disclaimer. But as we just went through with the Necker cube, you're continuously pushing against an app or a system, or your user is. They're observing what they see, and what do they do with that material. So in HCI, you will often see discussion of the twin gulfs, known as the gulf of evaluation and the gulf of execution. So let's imagine we have a certain goal, or your user has a certain goal when they're trying to play with your system. In this case, the goal is to build a mental model. So they click on a button on the phone, or they tap on the screen of the phone, and they see something happen. They then interpret what they see, and they then need to cross the gulf of evaluation. Did what I see help me towards my goal? Did it help me build up a better mental model of what's going on? Let's think of another example. Let's imagine instead of my goal being to build a mental model, my goal is to find the turn off new message notification item. I press some button at the top of the menu hierarchy on my new phone, and I see a new set of options. I now need to evaluate, am I getting closer to where that hidden function is? Or I'm trying to find that particular function, and I've clicked on the message button in the sub-hierarchy. Have I gotten closer to finding that functionality, or have I gotten further away? Am I making progress towards my goal or not? All of the visualizations you're going to be showing to your users in your ASL system is ultimately that sort of thing. Their goal is to learn the 10 digits of the ASL language. Did what you showed them on the screen help them towards that goal or confuse them? You need to show them something that helps them cross the gulf of evaluation. No, I signed that digit wrong, or yes, I signed that digit right, or I tried to click on that button on their system and it either did click or it didn't register my click. Did the system get me towards my goal? Once I'm here and I'm still trying to fulfill this goal, what do I do next? So I'm going down through the menu hierarchy and I still haven't found turn off new messages. I see that there are 4 new options for me at the current level of the hierarchy. Which of the 4 buttons do I click on? Which of the 4 possible actions that are available to me do I execute? I pick one, I try and cross the gulf. Hopefully the labels on those 4 buttons help me decide which of the 4 I should choose. And I choose it, and around I go. So your system, one way of thinking about an intuitive interface is that it helps the users cross these 2 gulfs. If they're trying to do something with your system, is it easy for them to figure out what they need to do next to get closer to their goal? And once they do something, can they interpret from what you print to the screen whether they have gotten closer to the goal or not? Make sense? Okay. Here's another example. So back to our starfish for a moment. It has the same problem, the gulf of evaluation and the gulf of execution. So the robot is trying to evaluate what it's just done, and figure out whether that has helped it get closer to its goals. Let's think about stage 1 of the experiment, where the robot is trying to figure out how it's put together. So its goal is to build a mental model. Right? So if it performs an action, did that action lead to more accurate self models? And it can cross that gulf by comparing the sensory information it got from its physical self to the sensor information it got from its virtual self. Right? So the physical robot does something, gets sensor data back, the physical robot stops moving, and it starts the machine learning algorithm that's trying to train this mental model. If these mental models are generating sensor data that is approaching the real or physical sensor data, then the robot is crossing the gulf of evaluation. It knows it's getting closer to its goal, which is an accurate self-model, because an accurate self-model produces sensor signals that are very similar, if not identical, to the ones from the physical robot. So far, so good? Okay. This one's a little bit more tricky, the gulf of execution. So the robot has these 2 mental models at a given point in time. The robot knows that both cannot be correct. So the robot has to decide what action, the physical robot has to decide what to do next. What should it do next? It says here, right, which is choose actions that cause my self-models to disagree. What does that mean? Can we be a little bit more specific? The robot is trying to cross the gulf of execution. The physical robot is trying to decide what to do next. What should it do?
It's testing hypotheses.
It's testing hypotheses, so it has two hypotheses here, mental model 1 and mental model 2. What action should it execute? What does it mean for two models to disagree here?
Trying to perform actions that break the mental model in comparison to the sensor data that we have.
Yes, but it hasn't collected that sensor data yet. This is what makes it tricky. So the robot wants to perform it, you're right, the robot wants to perform an action in reality that will generate sensor data that is, when supplied to its current models, gives back different sensor information, right? It is trying to generate sensor data that breaks the predictions of the current mental models so that they can be replaced by new mental models. But the robot doesn't have that sensor data yet. It's at the gulf of execution. It has to decide what to do. How can it increase its chances of performing an action that produces exactly that kind of sensor data? What is the sensor data? What are the two sensors that this robot has?
Touch and tilt.
It has touch and tilt, but we threw that away and we only kept the third one. Tilt, right? Which is vestibular, right? So how much it tilts left and right and how much it tilts forward and back. So what action should the physical robot perform at this point? It wants to get these two models to disagree. What does that mean? What is can we be more specific about what we mean by disagreement here?
Make the tilt be different for the actions they take.
Exactly. So, gulf of execution, I have 100 different actions that I'm considering at the current time, or 1,000 or 1,000,000, doesn't matter. I take each of those 100 actions, I supply it to this model, and I supply that action to this model, and action 1 causes both robots to tilt to the left. The tilt information is in agreement. So the robot throws away that candidate action, goes to the action number 2, takes that second action, supplies it to model 1 and model 2, and now model 1 rotates to the left and model 2 rotates to the right. They are disagreeing. Model 1 is saying, physical robot, I think if you perform this action, you'll tilt to the left. Model 2 says, no, don't listen to Model 1. Model 1 is wrong. I know that physical robot, if you perform this action, you'll tilt to the right. They can't both be right. The physical robot is either going to tilt to the right, tilt to the left, tilt to the right, or do something else. At least one of the models is going to be wrong, and we're going to break that model. And push through, help the machine learning algorithm push through and replace whichever model was wrong with a more accurate model. If the robot had performed action 1, which caused both robots to tilt to the left, and the physical robot tilted to the left, everyone was right. The robot hasn't learned anything new, right? And that's its goal, to learn something new and improve these mental models. This is basically describing the life of a teenager, right? I'm going to try and do all these things which I know are right on the line. I'm not quite sure what might happen. I want to see. I'm going to do dangerous things, things that I know my parents won't agree with, or this particular authority figure will disagree with. I'm doing something which is actually useful, which is building up my mental models of the world and self and social situations and so on. You can cross the gulf of execution by choosing an action that will lead to some result that you wanted, or you can choose an action for which your mental models are not sure what's going to happen, and assuming you survive that test, you've learned something, right? Okay. Nothing ventured, nothing gained, right? Okay. All right, so again, I mentioned we're doing a little bit of hand waving here because we know exactly how the robots are building their mental models. We know that humans have mental models or forward models. We're not quite sure what form they take, but we do know that we have lots of them, and they also operate at different time scales, right? So at the moment that I'm speaking, I have mental models that are making predictions that I'm going to hear my own voice at 100th of a second into the future. I have a second mental model, which is making predictions that hopefully I'm explaining myself well. And that mental model will be validated if you do well on the quiz tonight, although there is no quiz tonight, right? So I have a second mental model which is operating at a slower pace. I have yet another mental model which is making predictions about the final grades you're all going to get in this class. And I'm altering what I do, hopefully that you all get A's at the end of this class, right? Okay, you've got your new smartphone or you're playing around with a new app. You also have different mental models that are operating at different time scales, right? When you click a button or tap the screen, you expect to see something or hear something, or assuming you're holding the phone and it vibrates, you expect to feel something basically instantaneously. You might be sending a text or an email. You don't expect an instantaneous response to those. You have some expectation about when you're going to hear back, partly based on who you're sending the text or the email to, right? Other examples. When you're interacting with systems, what kinds of predictions are you making at different time scales?
Like if you put your hand over a burner.
That one, absolutely, right? You have a very short time scale, very important prediction. Let's limit our discussion to electronic systems. What other interactions do you enter into with an app where you have expectations at different time scales?
How long it takes for something to load.
Right, exactly, right? So if the wheel ever comes up, that's a signal to say, pause your mental model that's expecting an instantaneous response. Whatever you've just asked for, it's going to take me longer than instantaneous to do, right?
Well, even within that, I expect if I'm like loading local things, it to be faster than if I'm loading something from the internet.
And how do you know whether you're loading something that's local or cached or from the internet? It may be useful for the app to show you, which helps you calibrate your mental models, right? If you know you're requesting something from the web, you're not expecting an instantaneous response. But if the interface doesn't let you know whether you're asking for something that's local or from the net, you might get frustrated, right? You only have 2 seconds before you have to put your phone away, so you want to ask for something that's local, but you don't know. You click on something, up comes the wheel of death, and you're frustrated, right? So what you draw to the screen is often helping your users calibrate their mental models or calibrate their expectations about when they can expect response. You're also influencing your expectations by lots of other things, right? Your hopes, your dreams, your beliefs, your emotional state, your level of attention, how late in the day it is for you, all sorts of things, right? We're subjective beings. Okay, so the brain is a prediction machine. It spends a lot of its time trying to improve mental models, but they're not perfect, and that matters. Again, the interfaces that you create need to support our imperfect ability to form and use mental models, right? It's difficult to run a mental simulation. You can do it at a very coarse level, right? So you can make a prediction probably about what's going to happen at 11:40 in 8 minutes from now, but you can't really visualize your actual footfalls as you leave the room, right? You know how this is basically going to play out, but the details are very, very hard to mentally simulate. We forget things over time. Our mental models degrade. We're affected by bias and superstition, right? I've had 3 smartphones already, and function X was always at this point in the menu hierarchy. Now you've sold me phone number 4, and now the function is somewhere else, right? And you obviously adopt your mental models from previous systems and technologies and so on, right? So as you're building your ASL model, your users at the end of this course have probably never seen the system before, but what expectations are they going to bring to your system the moment they start waving their hand over the device? Okay. How can you help your users build up a mental model of what's going on under the hood?
Make things consistent.
Make things consistent? How so?
Like if you have if you have several different things they can do in the app, you make sort of the flows that they go through the app are very similar.
Okay.
That way they have to minimizes the number of actions they have to memorize, and kind of more quickly adjust to the understanding stage.
Absolutely, right? So that you try and get away with throw away all the extraneous detail, make everything consistent, very simple. Most users will twig to that pretty quickly, right, and appreciate it. I don't know if you remember the first time you ever saw the Google front page. I do. You realized immediately this was a whole new ball game, right? This company called Google was committed to they knew what you wanted to do. All you wanted to do was type in some keywords and get a list back, nothing else, at least to start with, right? You're already advertising something about your system in that case. I expect that when you click in Google, when you click on a button, it's going to stay simple at the next page. Maybe not as simple as the landing page, but that's something that's important in this system. When your user figures out to wave their hand over the device, they're going to see something that is telling them somehow to center their hand. Unbeknownst to you, a timer starts counting down from 10 to see whether they keep their hand centered for 10 time steps, right? I think that's in there. Is that right? Or is that to what is it?
That is to your discretion.
Or whatever, yeah, to your discretion, right? Whatever it is, you want the user to hold their hand there for a certain period of time. Your user doesn't know that. How might you communicate that?
And I made it so you couldn't actually progress to the signing stage until you held your hand over it. And if you move your head out of the center, it would go back to the initial state.
Okay, so I could see that, right? So something happens when my hand is near the center, and then I go back to something else when my hand is off. That might be enough to say, okay, it's trying to tell me to keep my hand there. But how long do I need to keep my hand there until I unlock the next thing that I can do with this system? I don't have any mental model here. I don't know how long I need to keep my hand there until it happens. I might be a patient user and wait indefinitely, or I may not.
At first I had a countdown that displayed.
Great, that helps, right? So if the countdown starts at 100 and starts counting down from there, that might be the end of my interaction with your system, right? It may matter. So you could do that. You could color the lines, right? The lines become increasingly green as the hand is over the device. Most people have an expectation that things that are becoming green are becoming more good, right? If my hand is drifting out of center, maybe the wireframe becomes more red. Whatever I'm doing, I'm moving away from what I'm supposed to be doing, right? I start to build up a mental model of this system, right? Whatever it wants me to do, if things on the screen are getting greener, then I'm doing the right thing. If things are getting redder, I'm doing the wrong thing. If I see a whole bunch of digits that start counting down to 0, okay, I get it. There's a whole bunch of timers here. There's things I'm supposed to do for a certain period of time, and I'll be told for how long I need to do it. There's different ways you can do this. Okay. Here's some other ideas. The book talks about a system image, which is kind of putting all of these things together. So a system image is the interface itself, the underlying philosophy, so the Google philosophy of keep it simple, or the philosophy of more green means better, more red means you're getting worse. System behavior, documentation. Most modern apps don't have documentation anymore, so we can kind of forget the last thing. We've already talked about visual metaphors, right? So I might see that there are a cluster of buttons, and I might start to realize that buttons that are closer to one another allow for similar functionality. Buttons that are further from one another imply different functionality. So distance implies semantic distance, meaning difference in functionality. Common things might have big buttons or obvious buttons. Rare or dangerous actions might have small buttons to minimize the chance that I will click on them by mistake. This especially matters in a gesture system where it's actually kind of difficult to actually indicate a specific action. What other kinds of visual metaphors might be useful in a system like this? Physical proximity implies functional similarity. Size implies importance or common. X implies Y. What might be X and what might be Y here? So let's think about your ASL system again. You are going to allow the user with their secondary hand to navigate through some menu hierarchy. What kinds of visual analogies or metaphors might be useful here? Let's say I have a horizontal row of buttons, so there are different things that I can do in your system. And I learn through some sort of interaction with the system that you don't want me to actually click on the button. It's more of a pointing thing. So if I want to click the leftmost button, what would I know that I need to do? What gesture is going to get that, is going to click that button for me? So the angle of my finger, right? So if I click further, if I point further to the left, I'm selecting the leftmost button. And if I hold that for 5 iterations through the infinite loop, the button clicks, right? So now I learned that the direction of my finger implies which button I press, right? And buttons to the right probably mean forward to future lessons or harder lessons, and buttons to the left maybe mean backwards or repeat. Because for most people that read from left to right, left means things in my past and right means things in my future. Okay, I think we'll leave things there for today. You do not have a quiz due tonight. You do have deliverable 8 due next Wednesday. Have a good weekend.